Hello, everyone, and welcome to the final episode of Act 1. Now that we've got the nuts and bolts of neural nets under our belt, it's time to zoom out and see how it all comes together in the real world. Over the next few slides, we'll cover three big areas. First, how deep learning became the bedrock of today's AI, powering large language models like GPT-4 and Claude. Second, the training toolkit, the data that fuels AI, the magic of self-supervised learning, and the art of fine-tuning and quantization to build and deploy models intelligently. Finally, we'll close with a small recap and some key takeaways, including what content you can expect to see in Act 2. We've talked about neural networks, and now it's time to go deeper. Literally. Deep learning means using networks with many layers, sometimes dozens, even hundreds. Each layer automatically learns features from raw inputs. In vision, early layers spot edges and colors, deeper layers assemble those into shapes and textures, and the deepest layers recognize entire objects. Likewise, in language, lower layers pick up characters and word patterns, while higher layers grasp phrases and semantics. This contrasts with the shallow approaches of old, where practitioners handcrafted features, like edge detectors or part-of-speech tags, then fed those into simpler models. Deep nets bypassed that manual work by learning hierarchical representations on their own, but the catch is they demand massive datasets and huge compute power, like large clusters of GPUs. However, those investments paid off spectacularly. After the 2012 ImageNet breakthrough, error rates plummeted as networks grew deeper. That shift from shallow to deep is what unlocked modern breakthroughs in computer vision, speech recognition, and natural language processing. One of the crown jewels of deep learning today are large language models, or LLMs. Think of an LLM as a transformer-based neural network with billions of parameters, pre-trained on internet-scale text via self-supervised learning, often by predicting the next word or filling in a masked word. So, what exactly is a transformer? Transformers are a type of architecture that powers many of today's large language models. At their core, transformers help the model understand the relationships between words in a sentence, or even across whole paragraphs, by paying attention to context. Imagine reading a sentence and remembering which words relate to each other, even if they're far apart. Transformers do exactly that, using something called self-attention to weigh the importance of every word relative to the others. This ability to focus on different parts of the input all at once lets transformers capture meaning much better than older models that read word by word. They process text in parallel, which makes training faster and more efficient. Because of this, transformers have revolutionized natural language processing, enabling applications like chatbots, translation, and summarization to work with impressive accuracy and nuance. For example, GPT-3 packed around 175 billion parameters and ingested roughly 500 billion tokens of text during training. As you scale both data and model size, performance improves in remarkably smooth scaling laws, and new emergent abilities, like basic arithmetic, code generation, or rudimentary reasoning, start to appear once you cross a certain size threshold. Today's LLMs, GPT-4, Claude, Palm, Llama, all share this recipe: transformer architecture plus massive data plus massive parameters. The result is a model that can generate human-like text, translate languages, answer questions, write code, and more, simply by predicting the most likely next words. As I mentioned during episode 1, they don't understand language as we do, but statistically, they've seen so many patterns that they can mimic understanding. These models have made natural language AI a household topic and set the stage for the rest of our exploration. Let's talk about data, fine-tuning, and self-supervision a bit more. Deep learning success stories all rest on these three training pillars. First, datasets are the fuel that powers model training. The mantra, garbage in, garbage out, holds true. If your data is noisy, biased, or too small, Your model will be too. We split data into training, validation, and test sets to measure real performance. Landmark datasets like ImageNet, with 1.2 million labeled images, and internet-scale text crawls like Common Crawl and Wikipedia enabled breakthroughs by providing the raw material. Second, fine-tuning has become the dominant workflow. Instead of training from scratch for every task, we pre-train a general model on broad data. Then we specialize it on smaller, task-specific data. It's like teaching a student general science and math, and then sending them to medical school for specialization to become a neurosurgeon. BERT, for instance, was pre-trained on unlabeled text and then fine-tuned on sentiment-labeled movie reviews to achieve state-of-the-art accuracy. Fine-tuning drastically reduces data needs and speeds development. Up third, self-supervised learning, which ingeniously turns raw data into its own training signal. No human labels needed. In language, we mask words and ask the model to predict them. In vision, we might mask a patch of an image or scramble it into jigsaw pieces before asking it to reassemble. Because the data already contains the answers, we can train on mountains of unlabeled examples, driving powerful representations without costly annotation efforts. Together, these three strategies form the backbone of modern AI development. Knowing them is key to building and adapting real-world systems. Now, before we ship any model to production, we have to be sure it learned real patterns, not just memorized the training data. First, we use 3 data splits. The training set is what the model learns from. The validation set helps us tune hyperparameters. These are the settings like learning rate or network size that control training behavior but aren't learned themselves. The test set is held back and only used once at the end to get a final honest performance score. A common problem is overfitting, when the training loss keeps improving, but the validation loss starts getting worse. This means the model is memorizing quirks or noise in the training data instead of learning generalizable patterns. The opposite problem is underfitting, when both training and validation losses stay high because the model is too simple or hasn't trained long enough. To fight overfitting, we use regularization techniques. One such technique, dropout, randomly silences neurons during training so the network can't rely on any single path. Another, weight decay, also called L2 penalty, discourages weights from growing too large. Then there's early stopping, which means we save the model checkpoint at the point where validation loss is lowest, and stop training before the model starts memorizing. After any combination of these methods, we need to measure success. And success is measured by task-specific metrics. You have accuracy and F1 score for classification tasks, blue and rouge scores for translation and summarization, which measure how well generated text matches human references. Then there's mean squared error for regression tasks, which measures prediction error in continuous values. Long story short, whatever the metric, we only report the number from the unseen test set. That's our best estimate of how the model will perform in the real world. To sum it up, the best model isn't the one with the lowest training loss. It's the one that balances fit and generalization, proven by strong validation and test scores. Let's talk about deployment, and why these training principles really matter. Quantization is an efficiency trick that converts high-precision 32-bit weights and activations into lower precision formats, like 8-bit, 4-bit, or even mixed precision. Doing so shrinks the model size, cuts memory bandwidth, and speeds up inference, making it possible to run large models on edge devices, phones, or modest GPUs, with only a small accuracy trade-off. Common quantized model sizes range from 2 billion to 16 billion parameters, balancing efficiency and performance. Why do you need to understand these concepts? Well, because data choices dictate what your model can learn and what it misses. Fine-tuning data lets you adapt a general-purpose model into a specialized expert. saving time and data. Self-supervision unlocked scaling to trillion token corpora, fueling the impressive in-context learning and emergent behaviors exhibited by today's LLMs. Finally, quantization ensures you can deploy these heavy hitters in the real world, from cloud servers to mobile devices, edge devices, or your gaming PC with a modest GPU. Together, dataset curation, fine-tuning, self-supervised pre-training, and model quantization comprise the full lifecycle of modern AI. Build, adapt, and deploy. Speaking of adaptation, because full fine-tuning of a multi-hundred billion parameter model can be prohibitively expensive, researchers developed parameter-efficient methods. One leading approach is LoRA, or low-rank adaptation. Instead of updating every weight, LoRA inserts small, trainable, low-rank matrices into each layer. This results in slashed GPU memory needs, and it cuts training time as well, while still delivering performance on par with full fine-tuning. There are other tricks too, like prompt tuning and prefix tuning, which freeze the main model and only learn a small set of soft prompt vectors. Think of these as virtual questions that steer the model's behavior. Other tricks, like prompt tuning or prefix tuning, freeze the main model and only learn a small set of soft prompt vectors. Think of these as virtual questions that steer the model's behavior. These lightweight techniques let you achieve specialized performance without owning a deep learning cluster. Mastering these methods is essential for making LLM customization accessible, from cloud VMs to even high-end workstations. Congratulations, you've made it to the end. So let's wrap up Act 1 with 7 bite-sized takeaways. First, AI is just math and code. We busted a few Hollywood myths and saw that today's systems are narrow specialists, not sentient robots. At least, not yet. Second, the 3 learning styles. Supervised is flashcards with answers, unsupervised is pattern hunting with no labels, and reinforcement is trial and error with rewards and penalties. Third, neural network plumbing. Layers, weights, and nonlinear activations flow forward. Backpropagation plus gradient descent nudge every weight until the error shrinks. Fourth, scale changes the game. When you multiply data, compute, and deep architectures, you unlock large language models like GPT-4 and PaLM. Fifth, data quality rules. Garbage in, garbage out still applies. Fine-tuning clean, domain-specific data turns a general model into an expert, while self-supervision lets us learn from oceans of unlabeled text and images. Sixth, deploy smart. Tricks like quantization and low-rank adaptation shrink models from 32-bit giants to 8-bit or even 4-bit, so they run on laptops, phones, and edge devices without much accuracy loss. Seventh, and most exciting, what's next? In Act 2, we'll dive into generative AI techniques, essential Python libraries, retrieval-augmented generation with vector databases, hardware choices, ethics and regulation, some of the latest frontier models, and finally, some hands-on project ideas. Thank you for sticking with me through this fire hose of information on the foundations of AI. I hope that I've helped you learn something valuable, and I can't wait to see you in Act 2.